All right, now let's look at an example. We have water at 373 Kelvin and 100 bar, and we want to estimate the fugacity coefficient and fugacity for this water. The following data is given. The second virial coefficient is given. This is B. This is the density for water, or rather inverse of density, I should say. This is in cc per gram, so this is actually the molar volume. So this is inverse of density, and then this is the vapor pressure, so essentially the saturation pressure. This is the information given to us. We can also call this as V, the specific volume. And based on this information, we are to calculate the fugacity and fugacity coefficient for water. This is liquid water at 373 Kelvin, right? So the first thing we do is we will write the equation we just derived, which reads the fugacity of liquid. I'll omit the subscript I, we just have one species anyway, is the fugacity at the saturation condition. So it is the fugacity coefficient times the saturation pressure times the Poynting correction factor, which reads exponential of the volume of the liquid P minus P sat over RT. This is the expression we have just derived. So we have to use this expression and calculate the fugacity of the liquid phase. We'll take each term at a time. P sat is given to us, so let's write what is known. P sat is given to us, it is 1 bar. P also is given to us, it is 100 bar. R is 83.14 bar Cc per mole per Kelvin, and the temperature is 373 Kelvin. The volume of the liquid is 0.958 cc per gram, but remember we work with molar quantities in all these equations, so this is a specific volume. What we'll do is we'll multiply it with the molecular weight for water, which is 18 grams per mole. So that will be equal to 17.24 cc per mole. This is the molar volume at the given condition. We have converted it from the specific volume to molar volume. So I have V liquid. So I have everything that I need to calculate the Poynting correction factor. The only thing that is missing in this, on the right hand side of this equation, is the saturation vapor pressure. How do we get the saturation vapor pressure? If you recall, we said at the saturation condition, because we are at equilibrium between the vapor and liquid phases, the fugacity of the liquid will be equal to the fugacity of the vapors, which we are calling it as the saturation fugacity or fugacity coefficient. So what we will do is we will use the vapor phase and the second virial coefficient to estimate the fugacity coefficient in the vapor phase, and we'll use that value for the saturation condition. So ln phi for pure species, if you recall, is Bp, and because we are at the saturation condition, I will use P sat RT. This will be fugacity coefficient at T and P sat for vapor. And once we calculate it for vapor, it's of course going to be same for the liquid as well. But this is how we're going to calculate the fugacity coefficient at the saturation condition. So B is given to us negative 452 cc per mole multiplied with 1 bar over 83.14 bar cc per mole per Kelvin multiplied with 373. And if I simplify this numerical value, what I will get is negative 0.01458. What that means is the fugacity coefficient will be exponential of this value, negative 0.01458, which will be 0.9855. This will be the fugacity coefficient. Now I have everything I need to calculate F liquid. F liquid, we said, is phi sat, P sat exponential V for the liquid, P minus Psat over RT. This value, the first value was 0.9855 times Psat is 1 times exponential of V liquid is 17.24 cc per mole times 100 is the value for pressure, 1 bar is the value for Psat, 83.14 is the value for R in bar cc per mole per Kelvin. The temperature is 373 Kelvin. With these numbers, the first two numbers, the product of those is 0.9855, of course, multiplied with the exponential value I have is 1.0566. So this Poynting correction factor, as you can see, even when the pressure changes by about 100 bar, the Poynting correction factor is only 1.05 for this liquid volume, and this is typically the case. For 100 bar, we have about 5% change in the molar volume for typical liquids we encounter in the industry. So this is the number we are looking at in terms of Poynting correction factor and the fugacity at saturation conditions, and once we multiply these two, we will get the fugacity of the liquid, 1.0413 bar. So as you can see, the fugacity of the liquid at 373 Kelvin and 1 bar, which is the saturation condition, is about 0.9855, and the fugacity of the liquid, when we change the pressure from 1 bar to about 100 bar, right, 100 bar is 1.0413, and like I said, it's about a 5% change. That's the only change we get for a change in pressure of 100, about 99 bar, right? So of course both these units are in bars, right? So those are the type of numbers we're looking at when we talk about fugacities of the liquid phase. This of course comes with the assumption that liquid is fairly incompressible, so going from 1 bar to 100 bar, the average molar volume will be more or less constant at that number of 17.24. If that's not the case, of course we see a slight change in these numbers, but they're fairly incompressible. Molar volume doesn't change much at these conditions. So that's how we use the concept of vapor-liquid equilibrium and use it in calculation of fugacity of the liquid phase via the Poynting correction factor. Now, once we look at this, this expression is going to be useful for the discussion we're going to do in our next section, right? The next section will be talking about the vapor-liquid equilibrium in general, how we go about modeling vapor-liquid equilibrium for non-ideal solutions, and how we collect experimental data to obtain the excess Gibbs free energy values. Remember when we talked about the excess properties, we said the excess Gibbs free energy comes from vapor-liquid equilibrium data typically, and the excess enthalpy comes from the mixing experiments. So we'll start our discussion on vapor-liquid equilibrium modeling for non-ideal solutions, and then look at how experimental data is collected to obtain the excess Gibbs free energy. Recall that the Gibbs free energy dGi bar, the partial molar Gibbs free energy, is related to fugacity of species I in a mixture via this relation, right? I can integrate this. This is at constant temperature. I can integrate this, and what we get is Gi bar is some function for that species I, some constant which is a function of temperature for that species I, plus RT ln Fi hat. Also recall that for an ideal solution, Gi bar ideal, we have written it as Gi plus RT ln Xi. Now, this is how we have defined an ideal solution. Now, if I can expand Gi, right, it will be, for a pure species, it will be the constant gamma I, it is same, it is only dependent on the temperature T and the species I. As long as it is the same species I and we are at the same temperature, then it will be same value of gamma I, plus, because it is for a pure species, all I will have is simply RT ln Fi, right? So this will be Gi. So then Gi bar for ideal solution will be gamma I T plus RT ln Xi Fi, right? And if you compare these two equations, what we get is Fi hat in an ideal solution should be equal to Xi times Fi, right? Both these equations are identical. One is written for ideal solution, one is a general equation. So what this essentially implies is that for an ideal solution, Fi hat ideal should be equal to Xi Fi, and we call this as Lewis-Randall rule. So in an ideal solution, the fugacity of species in the mixture is going to be proportional to the pure component fugacity, or it's going to be proportional to the mole fraction, and the constant of proportionality is of course the pure component fugacity, because at one end it has to be the pure component fugacity, right? And we call this as the Lewis-Randall rule. So if I were to draw a picture of Fi hat ideal in a binary mixture, let us say this is x1 going from 0 to 1 and this is F1 hat, right? If I were to draw how F1 hat changes with the composition x1, it will look something like that. At one end, when x1 is 0, F1 hat is going to be 0 because of Lewis-Randall rule. At the other end, it will be same as F1, that is for pure species 1. So this is of course only true if Lewis-Randall rule is valid or if it is an ideal solution. F1 hat ideal will look something like that. That is how it changes with mole fraction of that particular species in the mixture. In general though, if we take these two equations here, right, for a non-ideal solution, if I take this equation 1 and this equation 2, right, and I subtract one from the other, what I get on the left hand side is Gi bar E. That is the excess Gibbs free energy. Gi minus Gi ideal is the excess Gibbs free energy, is going to be equal to RT ln Fi hat over Xi Fi. Or if I were to write it in a better way, Gi bar E over RT is going to be ln Fi hat over Xi Fi, right? We call this quantity on the right hand side as gamma I, or the activity coefficient. So let's rewrite that equation one more time. Gi bar E over RT is equal to ln of Fi hat by Xi Fi, and we'll call that as activity coefficient gamma I. It is the ratio of the fugacity of species in the mixture over what is given by the ideal solution. So it is Fi hat over Fi hat ideal, right? And we call this as the activity coefficient. Obviously, gamma I equals 1 for an ideal solution, because Fi hat will be equal to Fi hat ideal. Otherwise, it will not be unity, will have value that is not equal to unity, and that number will denote how non-ideal the solution is, right? If it is 1, we have an ideal solution. If it is not 1, we have a non-ideal solution, right? And also note that Gi bar E over RT is a partial molar property. So Ge by RT will be equal to sigma xi gi bar E over RT. This is using the summability relation, right? If we add the partial molar properties multiplied with the mole fraction, we get the total property. What this means is GE over RT is going to be sigma xi ln gamma I. So if I know the activity coefficient of the species in the solution, I can calculate the excess Gibbs free energy for that particular solution. We'll come back and see how we can obtain this value of gamma I from experiments. But that's the essential idea of introducing activity coefficients. Just like a compressibility factor, for ideal gases it is 1, for non-ideal gases we deviate from 1. Similarly, for ideal solutions the activity coefficient is 1, for non-ideal solutions we're going to deviate from 1. And like we said, the excess Gibbs free energy itself can have positive or negative deviations from ideality. Similarly, gamma I can be greater than 1 or less than 1 depending on whether we have positive or negative deviations from ideality for that particular solution. Now, since we talked about the excess Gibbs free energy and fugacity of and how the fugacity of species in a solution is related to the excess Gibbs free energy, now let's go back to our original problem of how to obtain GE by RT from vapor liquid equilibrium data. To do that, what we need to do is formulate the vapor liquid equilibrium problem. If you recall, we said for vapor liquid equilibrium, mu I in the vapor phase should be equal to mu I in the liquid phase, or Fi hat in the vapor phase should be equal to Fi hat in the liquid phase. We have derived this equation. We said the chemical potential should be equal, or in other words, the fugacities of each of the species in both the phases need to be equal. Now, let's take each one of these fugacities and see how we can obtain them. The vapor phase fugacity is fairly straightforward to obtain. What we'll do is we'll write it as the fugacity coefficient of that species in the vapor mixture multiplied with the partial pressure of that species Yi times P. At low pressures for most of our industrial applications, we might be able to use now this fugacity of species in the vapor at low pressures. Most gases behave as ideal gases, so the fugacity coefficient for the species can be approximated to 1, and if we do that, the fugacity in the vapor phase will simply be equal to Yi times P. Now, when we look at the fugacity of the liquid, we said this will be by definition of the activity coefficient. So let's write gamma I first, multiplied with the fugacity of the ideal solution, which is Xi times Fi. Fi is the fugacity of the pure species I. And for the pure species I, we can write that fugacity as the fugacity at the saturation conditions, phi I sat, pi sat, multiplied with the Poynting correction factor, P minus pi sat over RT. And as we have seen in the example we worked, using the Poynting correction factor, even for a change of 100 bar, the Poynting correction factor is less than 5%. For smaller changes, the Poynting correction factor can be safely ignored for smaller changes from P to pi sat, that is. And if the saturation pressure also is low pi sat and P minus pi sat also being, or the difference between P and pi sat also being low, what we can do is we can safely ignore the Poynting correction factor, and we can also assume that the gas phase itself is going to be ideal, so we can ignore the fugacity coefficient at the saturation condition for the vapor phase because pi sat itself is low. And if that happens, we can approximate Fi hat liquid to be Xi gamma I pi sat. Now remember, for this to happen, the vapor phase at the saturation condition needs to behave as an ideal gas, and the Poynting correction factor should be small enough that we can ignore it. And when that happens, Fi hat liquid will be this. So once we have this, we can equate the vapor and liquid phase fugacities with the approximations we have made. That equation becomes xi gamma I pi sat will be equal to yi times p. If we only ignore the Poynting correction factor and do not ignore the non-idealities in the vapor phases, then this equation will become xi gamma I pi sat times phi sat for non-ideality at the saturation conditions will be equal to yi p times phi hat for the vapor phase. So depending on the pressures and the saturation conditions, we will choose one of these equations and try to work with them accordingly. So what we have done via this exercise is we have related the vapor and liquid phase fugacities in terms of quantities we can easily work with. The only thing we still didn't talk about is gamma I, the activity coefficient, which we related it to the excess Gibbs free energy. Now remember, when we said one of the ways to obtain the excess Gibbs free energy is using the vapor liquid equilibrium data. So if you look at the previous equation, or the simplified version of the previous equation, it reads YIP is xi gamma I pi sat when we ignore the non-idealities in the vapor phases. When that happens, this means gamma I is going to be YIP by xi pi sat. I can perform a vapor liquid equilibrium experiment, obtain the composition of the liquid phase, which is xi, the composition of the vapor phase, which is yi, the total pressure P, and I know the pure component vapor pressures Pi sat. And if I have this information, I can calculate the activity coefficient gamma I. And once I calculate gamma I, remember we said GE over RT is sigma xi ln gamma I. So I can do an experiment. I can take a closed vessel, fill it with pure species, and put it in an isothermal bath, note the pressure. That will give me Pi sat at that temperature. Change the liquid, but it will give me P2 sat. The first one was P1 sat. And then I can put a mixture of both the liquids and allow it to attain equilibrium. And at equilibrium, I will have both the liquid and the vapor phases, each with different compositions. The vapor phase composition is yi, the liquid phase composition is xi. I can sample them, obtain the composition or mole fraction in the vapor and the liquid phases. And once I have all this information, I can go back and calculate the activity coefficient. And once I have the activity coefficient, I can calculate the excess Gibbs free energy. So this is one of the ways to obtain excess Gibbs free energy using the vapor liquid equilibrium data in this case. Once we have that information, we can build models for excess Gibbs free energies, just like we have equation of state for PVT relationship. We can build a model that relates excess Gibbs free energy to the compositions. And once we have that model, we can use that to obtain the fugacity coefficients and obtain vapor liquid equilibrium behavior for that particular mixture. Let's talk about one final thing before we stop the lecture today. This relates to the behavior of the systems at the ends of the composition diagram. We said that the fugacity varies with composition F1 hat, varies with composition linearly if it is an ideal solution. This is F1 hat ideal, and this value then needs to be F4 pure one at the temperature and pressure of interest. But in real life, the solutions are not ideal. If they are not ideal, F1 hat ideal will not fall along this line. It might look something like that, right? So let's join that. So there is a deviation from ideality for F1 hat. Nevertheless, at the ends of the composition, limit x1 going to 0, f1 hat should go to 0, and limit x1 going to 1, f1 hat should approach f1, right? The other thing we can note from this particular diagram is sigma xi d mu I is 0 because mu I is a partial molar property and Gibbs duhem equation has to hold at constant temperature and pressure. Since d mu I is dgi bar, mu I and gi bar are same, is RT d ln fi hat. What this means in a binary system is x1 RT d ln f1 hat plus x2 RT d ln f2 hat should be equal to 0. We can get rid of RT. So what it means is x1 d ln f1 hat over dx1. f1 hat varies with composition, either dx1 or dx2 in a binary, it doesn't matter, plus x2 d ln f2 hat with respect to the same x, x1 in this case, equals 0. This means x1 over f1 hat d f1 hat over dx1 plus x2 over f2 hat times d f2 hat over dx1 should be equal to 0. So this is a requirement because Gibbs duhem equation always needs to be satisfied. So f1 hat and f2 hat in that sense are not completely independent. They are somehow related to one another. So let's rewrite that, re-emphasize that again. So this equation 1 is the Gibbs duhem equation. Now, at the limit of x1 going to 1, the solution becomes ideal. We have mostly pure 1 and the excess Gibbs free energy will be equal to 0, and because the solution becomes ideal, f1 hat will be equal to x1 times f1 because that's the property of an ideal solution as we have seen a minute ago. When that happens, the limit at x1 going to 1, x1 over f1 hat d f1 hat over dx1 will be x1 by x1 f1, and the derivative of f1 hat with respect to x1 will be f1. So this value turns out to be 1. Now from 1 and 2, 1 is applicable everywhere, 2 is applicable at a particular limit. So limit as x1 going to 1, x2 will go to 0 at this limit, x2 over f2 hat d f2 hat over dx2, and the first term at this limit is 1, so 1 plus this should equal 0, or what this means is limit x1 going to 1, x2 going to 0, x2 by f2 hat d f2 hat over dx1 should be equal to negative 1. Now recall that x1 plus x2 in a binary system is 1, so dx1 plus dx2 is 0, or dx1 is negative of dx2. So I can easily replace this dx1 here with dx2, and what that means is limit as x2 goes to 0, df2 hat over dx2 times x2 over f2 hat will be equal to 1, or limit as x2 goes to 0, df2 hat over dx2 will be equal to f2 hat over x2. What this means is that the slope will be same as the ratio of f2 hat to x2, or f2 hat will be the slope, whatever that value is, multiplied with x2. We call that slope as h, or the Henry's constant. Let's see what it means. Let's draw a diagram of how things change with composition x1, 0 and 1, And what I'll do is I'll also indicate x2 on this particular diagram. x2 is 1 here and 0 here. And let me write f1 hat here. f1 hat, when this is 0, will start here. And as we have seen, the ideal solution line or the Louis-Randall line will go like this until this point, which is f for pure 1. If the solution is non-ideal, it will go like this and then go like that. Now, as you have seen here, limit as x2 goes to 0, f2 hat is h times x2. Similarly, at the limit as x2 goes to 0, f2 hat is some constant h for 2 times x2. Similarly, limit, we can also show that limit as x1 goes to 0, f1 hat will be h for 1 times x1. So that is the slope of this line for f1 hat at the 0 composition. So if I draw the slope here, right, that's the slope. That slope will meet the line x equal to 1 at h1. This h1 is called as the Henry's constant. These are the two limits at the compositions going to 0. The other two limits we have seen are at the compositions going to 1. Limit as x1 goes to 1, f1 hat will be an ideal solution, so it will be x1 times f1. Similarly, limit as x2 goes to 1, f2 hat will be equal to x2 times f2. So these are the two ends of the composition diagram. What I have shown here is for f1 hat, we can draw a similar diagram for f2 hat. In that case, we will have the slope to be the Henry's constant for species 2 or H2, right? We have obtained this using the Gibbs-Duhem equation. What it means is that in the region where f1 hat is proportional to the composition x1, which is in this region, at the same region f2 hat, because x1 is going to 1, in the same region x2 is going to 0, in the same region f2 hat also needs to be proportional to x2. This is stipulated by the Gibbs-Duhem equation. So let's write that down. If f1 hat is proportional to x1, then f2 hat will be proportional to x2. This is a stipulation we can obtain from Gibbs-Duhem equation. The constant of proportionality here will be the pure component fugacity at one limit as x1 goes to 1, and at the same limit the constant of proportionality as x1 goes to 1, it is almost pure 1. We have infinite dilution of 2, and the constant of proportionality at infinite dilution, we are going to call it as the Henry's constant for 2H2. Similarly, at the other limit, at x2 going to 1, we have almost pure 2, so f2 hat will be x2 times f2. The constant of proportionality is f2, and as x2 goes to 1, x1 goes to 0, we have infinitely dilute 1, and f1 hat will be x1 times h1, or the Henry constant for 1. So this is the overall summary of how the fugacities are going to behave at the two ends of the composition diagrams. And as you see, the fugacity of both the species are related. They cannot independently behave. So with that, we stop the lecture today. When we come back, we'll try to look at the application of what we have derived today in terms of activity coefficients and how we go about using this data or using this model for obtaining the vapor-liquid equilibrium behavior. Thank you.